the 2021 NCLab webinar series, Exploring the NCLab Sampler Mini-Courses. Webinar number 2, Visual Intro to Python Mini-Course. This webinar series is made possible by a Nevada State Library, Archives, and Public Records continuing education grant funded by the Institute for Museum and Library Services through the Library Services and Technology Act. My name is Sheila Crawford Bunch, and I'm your host for this webinar. I am the Director of Education for NCLab. NCLab is pleased to provide content and support for the libraries in Nevada that will help Nevadans learn about and find jobs in our new technological world. I encourage you to follow along and try the sampler. You can find it in your desktop account in the Samplers course folder or in your browser at nclab.com/samplers. This webinar was recorded on June 24th, 2021. The samplers/mini courses are all found in the courses folder. Typically, if you are working on a course and you open your desktop, it'll automatically open to the first unfinished level in whatever course you're working on. But we'll do it from scratch here. So you can see over here you have courses, and this particular desktop is only loaded with samplers and mini courses. We'll open that folder and you'll see all the samplers and mini courses here. Now, just so you know the distinction, the ones that are mini courses are have less demos in them. You could take them and learn a little bit about computer programming or SQL. The other ones are a mixture of levels that you solve independently and some demonstrations of what the program can do. So for example, when you get into the advanced levels of Visual Python or data analytics or Python, a person just coming in cold would not know how to write those kind of programs. They're fairly complex. But it's kind of nice to see a look forward to see what you'll be learning towards the end of the course. So we'll go ahead and open Sampler Visual Python, and it'll pop open at the first level. And you can see that there are 10 levels. If I press the Home button, it'll give me a view of all 10 levels with a little description below them telling you what's in that level. And you'll notice that the only level that's open is level 1. You have to solve each level in order to unlock the next level. We'll go back to level 1, and there's a short tutorial that introduces the program. The way it works is you're going to be writing code in Python and using it to guide a drawing turtle. Drawing turtles go back to the 1960s or even further back. Turtle robotics goes back to the 40s. When scientists were studying robotics, they looked to several animal forms as a model, and turtle robot got the name because it had 4 wheels, it had a forward sensor, and it had a shell like that kept the electronics and the motors and everything clean. And then later on in the 60s, when MIT adapted the turtle to a drawing turtle, they had a pen coming out its rear end that looks like a tail, and as the turtle moved and turned, it would make a drawing. And even back in the 60s, they were looking for ways to teach kids how to program or beginners how to program. And they realized back then that it's pretty nice to have a visual output. It's much easier to see whether your program has worked or not if you have something relatable as an output rather than, say, zeros and ones or assembler code or just miles and miles of text. So the turtle that we're using is a Python turtle, and of course it's not physical anymore. It's just a graphic representation of one, and you can see that it's sitting on an XY coordinate plane. The red axis is X, the green axis is Y, And there are what we call default positions. So unless you tell the turtle to be somewhere else, it'll always start on the origin. That's the same as saying x equals 0 and y equals 0. And it will always face in the positive x direction. And just to make it more relatable, we also give these compass directions. So if you were looking at a compass, this would be east, that would be north, that would be west, and that would be south. So that's one way to see it. And then in coordinate terms, this is facing the positive x direction, north is facing the positive y direction, west is facing the negative x direction, and south is facing the negative y direction. So she's pointing east, and we just give it a default color. And the inside of the turtle will always show you what color it's set to. The default is blue, so you can see this turtle is blue. The other default is that the grid spacing, so you can see there's the axes and then there are the little gray lines, and each of those intervals is 10 steps. So that's when you're counting how far the turtle should go. It's 10 for every one of these steps. You always start out by doing what we call spawning the turtle. We are creating an object from a class called NCLab turtle. And you see the little parentheses after that. That just gives you an opportunity to put some parameters in there or arguments. For example, if you didn't want to start Tina at 0, 0, you could put a set of coordinates in there. But for now, all you have to do is type a name and make it equal to NCLab turtle with the parentheses. So you always have to spawn the turtle, and then to see what the turtle has drawn, tina.show. And so this simple program will spawn the turtle and display her. And let's just run that. You'll notice that you can't move forward until you've explored all the examples or links. So I'm going to open that up. And there's some instructions on how to use these controls. Okay, there's the play, the step. This is stop if you're in step mode. This will inspect the debugging tools. It tells you what variable types you're working with, for example. This erase button will erase all the code you have except for any pre-code that NCLab has put in there. And of course, this will close the window. So let's go ahead. The code's already written for us, and we'll run it. And it takes a few seconds to communicate with the server. And there it is. Now, this side is a viewer, so you can view the turtle in different dimensions, and you can zoom in and out. So if I wanted to make that area bigger, I can do this. Mouse controls work as well. We'll get into that a little bit later. Okay, I hit restore and I put it back the way it was. We'll just close that and keep moving. So the first thing you're going to learn how to do is draw a line. The command is go. Forward also works in this program. And then you're going to tell it how many steps. And here we've written 30. Now remember that each of these intervals is 10. So if we want Tina to move 3 intervals, it's 3 times 10 is 30. Remember again, the default color is blue. So let's go ahead and run that. And you notice this time there's an encouragement to play with it. So that's 30, 10, 20, 30. Let's change just this argument here to 40. And now we got 10, 20, 30, 40. And then they suggest 80. We'll run it again. And this time we got 10, 20, 30, 40, 50, 60, 70, 80. All right, that's easy. So we know that when we want Tina to move forward, we use tina.go, and then we specify how far with the number in the parentheses. Now, when you're producing a drawing, it's nice to have the turtle icon while you're working on the program because you can see where the turtle is and if it's turned a certain angle. So in other words, what directions it's facing. But at the end of the day, if you just want to produce a drawing, you also want to hide the turtle. We have another command that we put before the show line, and that is tina.hide. And you can see these are all written the same way. It's always tina dot something, and it always has parentheses after the command, but those don't necessarily have to be filled with information. So again, let's run that. And we got that result. Now, it's got some suggestions on how to play with this. And you'll notice that it says insert the hash symbol. In old-fashioned days, that was called pound. Put it in front of the hide command. So it shows you how to do that. So let's go ahead and put that in front. Where's my symbol? There it is. Okay, and you can see how it turned light gray. That means now the program is going to ignore that line. So this is a very handy tool when you're debugging a program. You want to just see how certain lines run, maybe hide the others. Then you can run it. And as you can see, the turtle's still there, so the program ignored hide. When you're working with a group, really have them work through the suggestions in the example. They'll get a lot more out of what they're trying to do if they follow those. All right, now do we have to call it Tina? Nope, it can be called anything. And this person here has named their turtle Jordan, and so it'll work. There's an R2D2. So you can call it anything you want and it'll work. All right, so we've worked through a few different skills so far. Now we come to a page where we're going to practice them. So this time, instead of just maybe tweaking the code here and there, we're actually going to write it. Oh, look, that's scary. There's nothing there. So if we remember how this worked, we're going to name the turtle, and I'll just stick with Tina for now. Good style is to put a space between operators. So I put Tina space equals space, and then I'm going to write NCLab turtle. Oh, that looks weird. I bet that won't work, but you know what? I'm going to try something anyway. Okay, it says just to display it. Okay, so show turn to color. I thought this was going to turn a color. I'm going to run it and see what I did wrong here. Oh, it says name error, name NCLab turtle is not defined. Huh. All right, well, if I go back and look at the previous exercise, I'm going to discover that that's got a capital. And look at that. It also changed colors. So when you're calling an object class, that's the class, you have to use capitalization exactly the same way it's used. So if I do it right, it also changes color. So now it looks a little different, and if I run it this time, hey, it worked. Yay. Now I'm going to make a mistake that will get caught by the grader after I submit the code. I want go and let's say 20 or something. 20. All right, so I'm going to run it. I didn't follow instructions, did I? It said I should have 2 lines, and I've got 3, and I'm making the turtle move, and I was being way too creative. Okay, I produced a nice result. My program runs. It's a good program, but when I go to submit it to the grader, dun dun dun. Oh, the grader doesn't like me. It says the trace is not correct. The correct trace is shown in green. Your solution is shown in red. It may be hidden inside the correct solution. Well, we know that the turtle's not supposed to move, and probably that's not enough to produce a green trace. But yeah, it didn't like me adding that line. That's not following instructions. So I'm going to go ahead and take advantage of my nice little hash symbol and run it again. And the program should only see 2 lines. Let's see if it does. Yes, good job. Okay, it passed all tests. Now, when you're doing these exercises, and you have to keep in mind these are exercises as opposed to a graded task. If you really can't figure it out, there is a hint, first of all. Okay, it'll tell you some stuff. So when I was having trouble with that name, I could have clicked on the hint and it would, oh, there's a capital T for turtle and it's supposed to turn red. Okay, got it. All right, so you can look at the hints, and if you really still can't produce results, there's the solution right there, and you can use the code. You just paste it in. You can see how it pasted it in. So for the exercises, you have the answers and you can submit them. Now, the moment you close an exercise, it's not going to save your work. It's really meant to be reused for practice. So if you really liked a script, you might want to save it to a text file for your own interest sake. Okay, so you notice I've done exercise 1 and now I have a green check mark. I'm going to do exercise 2. Okay, so this time it says spawn the turtle, draw a line of length 60 and display it. Your program should have 3 lines. Okay, so you have the idea on how these work. They build. So the first one was 2 lines, the second one was 3, and the third exercise adds that hide command. So we've got spawning a turtle, drawing a line, and gives us the length. We hide the turtle and we display the result. It should have 4 lines. You can type it in here. And so you get lots of practice. It builds from one exercise to another. All right, so then we go to what's called the graded task. And this is a task that if you do it, once you've finished doing it successfully, you run it and submit it and it passes, it gives you a grade. So what do I have to do? I have to spawn the turtle, draw a line of length 45, hide the turtle, and display the results. It should have 4 lines. And oh, you notice I don't have a solution anymore. I do have this new button called Code History. So let's build a little history here. We're going to start with making our turtle. Okay, and then I'm going to do what's called building out. So I'm going to follow the way we did it in the exercises. My next one's going to be show, and I know that with those 2 lines I can get some results. So I'm just going to run that. All right, there we go. And if I go to code history, you can see that I have run the program once, and that was my code. All right, I'm going to now insert a line, and it told me to go 45 steps. Yep. Oops. So I'm going to go 45 steps. And you notice I could just go to this line and press enter, and I got a new place to write. Tina, go 45. I'm going to run it again. Now this is a dead simple program, but you can see how I can test it as I go. And there's 1, 2, 3, 4, and she's in the middle here. That's 45. If I look at my code history, now I've got 2 runs. Okay, so if I ever needed to go back to a run, let's say maybe my internet was interrupted and maybe the server didn't quite have enough time to save my last run. I could go back to a previous one and use that using the code just like I would with the solution and start from there again. Okay, so we're going to finally go hide the turtle, and we know that goes in between go and show. Tina hide, and I'll run it again. And I'm pretty happy. This is what I wanted. The line is 45 in length. Um, and the turtle's not there. And it shows the results. I'm going to submit it to the grader. And I got 100%. Yay! All right, so now when I look at my code history, it tells me I submitted it once. So if I look at my whole history, I've got 1, 2, 3 runs and 1 submit. After the graded task, there is usually a discussion that will discuss the task. It might bring up another point or two, and then you're on to the next level. It's the same pattern. You're going to have an example that you explore. You'll have some instructions on how to do things. You'll have some exercises to try out your skills, and you'll have a graded task. Now it's time for you to try the first 3 levels. Pause this video, and when you're ready, come back and resume. Please try the examples and the exercises as well as the graded tasks. We'll see you in a little bit. Welcome back. Let's review 2 and 3. We already went through 1 together, but we'll review levels 2 and 3 before you go back to work on your own on levels 4 through 7, which all have to do with for loops. So in level 2, you learn how to make turns, and you notice that the argument for the turns is in degrees, and you can put in any number of degrees. This is an opportunity if you're teaching, say, a group of kids from upper elementary or middle school or even high school to review degrees with a protractor. You can have a handful of protractors out ready to look at and maybe do some drawing on paper to get a manual feel for what the program is doing. And also you're now learning how to set the color. Remember the default color is blue, but you can write in a color. And for now we're just using the colors that come with the program, and there's all the basics like purple, black, yellow, etc. and a few fun ones like banana and teal and brass. You can also create your own colors from RGB or hex code, but for now just play with the ones that are in the program. And just like the other keywords, they'll change color if it's a recognized keyword. So you can see here the word yellow is a slightly blue color, and that means it does exist in the program as a keyword. You always change the color before the command where you want the line to be drawn in that color, and you can change it again. So you can see here we had yellow and then drew a line and turned and then changed the color to cyan and did the same thing, and then green and so forth. So you practice those, and we're not just going to draw plain lines anymore. We're going to draw some shapes. Again, something that might be fun, and if you have a club going, is to get some manual Tetris pieces so that they can play with them physically on a game board. Or you can also refer to a very popular Tetris game for reference. This does give a link to the Wikipedia page that teaches something about the history. It's a very famous computer game. In this case, with the task, you're drawing the green Tetris piece, and you can see you're drawing quite a number of lines with the turn in between. So it's just a good exercise in drawing lines and turning angles. There's the discussion for that task. There's quite a few lines of code, and afterwards you have an opportunity to create a 3D piece. And in order to do that, you use the command Tina extrude, and that will give it a third dimension, a height. Extrude automatically hides the turtle, so you no longer need the hide command. You can print it out. I'll show you in the viewer where you can create an STL file. And an STL file can be printed on any 3D printer. Level 3, now we're using another command, go to, and the reason for go to is that you're not always drawing nice straight lines along the axes where the turns are pretty simple. You draw a line in one direction, you make a 90-degree turn, draw it in another direction. When you're drawing from point to point, it's very difficult to estimate the length of the line, but it's very easy to tell the program what points you want to draw to. So this is very good practice with XY coordinates in the coordinate plane. And you can see in this case, this is a little diamond or kite shape, and it starts at the origin at 0, 0. It goes to 20, 20, and then to 0, 30, and then to minus 20, 20. So these coordinates are always the x coordinate first and the y coordinate second. And that's great practice again for students who are learning the XY coordinate plane. This is a very fun way to practice their skills. This is just showing how ugly the program's going to look if you try and just use the go and the turns. Both your angles and your distances are nearly impossible to get accurate. So the go to command takes care of that. But just keep in mind the go to command is doing a lot of heavy duty computation in the background, so only use go to when you need to. There's a little theoretical explanation for it, and you get to practice. And for the task, this time you're going to draw a rocket. It says use any color of your choice. Personally, I find the yellow a little bit hard to read, so I tried it with orange, and I'll show you. I made a mistake. I'm going to run my program here. And you can see, I'll zoom in a little bit and recenter it, that the bottom of my rocket looks wrong. Well, what did I do wrong here? I started at the origin, and that's where Tina starts, and then I went to 10, 0, 10, 0. Oh, I should have gone 0. No, I should have gone 10, 10. So I should have gone over x10 and then y10. So this is super easy to change here. But can you see how this visual output really helps you correct your code? Whereas if you were just writing code without any kind of obvious output, you might have a lot more trouble debugging it. So that's why Visual Intro to Python is such a great course. You learn how to write in Python, you learn a little bit of math, and you have a nice debugging tool built into it. So I'm going to run it again with that change. And yeah, now that looks like the rocket. I'm happy, and it told me I can use any color, so I can keep it as orange. And I'm going to submit it. Oh, it's very happy. I got 100% again. Now, what you can see here is that I was able to fix my program before I submitted it to the grader based on checking the output and comparing the output to the expected output up here. So this is something to emphasize when you're running a club is you always want to run and check as many times as you need to be pretty sure that you've followed all the instructions and have produced the expected output before you submit it to the grader. One last point again is that these grid intervals are 10, so your coordinates, I know I made this mistake too when I was working on it. You think I would know better, but I was going 1 or 3, 1 and so forth, and I realized, oh yeah, those are supposed to be 10 each, so I went back and fixed them all. So anyway, there you go. That's that particular level. There's the rocket extruded. Oh, let's go back and extrude our rocket. So let's change hide to extrude. We'll run it again. Might take a little longer to compute. Nope. Okay, so now we want to see it in 3D. You notice these settings at the top. It'll show this result, but I can go to 3D, and there's my rocket. Nice. Okay, so if I wanted to, I don't know, for whatever reason, make that as a cookie cutter, we'll get into width a little later, but I'm just going to go ahead and, just for fun of it, make it thicker. Or, oh no, I need height for that. Well, I'm going to give it a little bit bigger width, and I'm going to use height, and I'm going to make that 10. I don't need extrude if I use height, so I'm going to comment that out. Let's see what happens. All right, so now I've got a little cookie cutter maybe. You see that? So I could print that on a 3D printer, and now I would have a cookie cutter rocket. And in order to print it on a 3D printer, I'm going to hit this export and save it as an STL file. Now, it's nice to save it in NCLab because that keeps it in your cloud file folder on your desktop. So if you wanted to go back and play with it a bit more, you could. But ultimately, you're going to save it to disk, so maybe a thumb drive or a server drive or your local hard drive, because you're going to want to take that file to your printer in order for it to print out. So there we go. We made a cookie cutter out of our rocket. All right. So now you're going to go on and start working with the for loop. The for loop is an incredibly important control structure in Python. If you did Carol or the Intro to Computer Programming course, you're already familiar with the repeat loop, and that was just repeating a set of actions a fixed number of times. You put repeat and then a number. The for loop behaves exactly the same way. Again, this is a visual course, so we're looking for patterns that we can repeat. In real programming, it's amazing how many times you have to repeat a procedure. So whether you're working on an assembly line and you're making the same part over and over again, there's a series of steps that you use to finish that part, and then you send it down the conveyor belt, and then you get the next pile of bits and pieces and you assemble the part and send it down the conveyor belt. Each of those is a loop. Another analogy is knitting. You knit a row of stitches, so you have a certain pattern that you have to knit to make a stitch, and then you repeat that so many times to the end of the row. And then there's a nested loop in knitting where you have a certain number of rows of that pattern. So there are lots of real life analogies of repeated patterns. I think if you start thinking about them, you'll find them everywhere. And they're again very important in programming. So go ahead and read through and do the exercises and the examples and the graded tasks from level 4 all the way through level 7. And it might take you a little longer than the first 3 levels, but I think you'll learn a lot, and we'll review them when you come back. Hi everybody, welcome back. I suspect if you typed all of these exercises and tasks by hand, in other words, not copying and pasting, that you're pretty fluent now on creating an instance of the class and writing each command and making sure that you're using the correct command names and that your arguments are the correct number of either steps for go or degrees for the angles. Just a quick mention, in the last exercise I think I used the Tina height command. That's something you can use ahead of your code just like you do width to set for the next set of lines, and then if you want to you can change height for another set, so you can make some pretty interesting figures that way. For these exercises, extrude at the very end is just fine. You don't have to use height. You can use extrude, give it the same number, it'll do the same thing. All extrude does is it gives it that third dimension to every single line at the same time, everything you've already drawn, so it applies to the whole drawing. Um, this opens up with a look at the yellow square, which was pretty straightforward. You're going 20 and then you're turning 90, and you do that 4 times. You go 20, turn 90, go 20, turn 90, go 20, turn 90, go 20, turn 90. You end up back at the starting spot. You can't overemphasize the value of for loops in Python. This is an important point at the bottom of the page here, that computer programs should never contain repetitive code. There's a bunch of reasons for that, but the main one is that it's really easy to make a mistake. And if you have to find all the times you've repeated that mistake, it's a mess. If you have them controlled in a control structure like a for loop, you can fix a problem once and it will apply to all the repetitions. It's very nice. So here's the suggested for loop, and let's just open that up. Let's say I did make a mistake. I wrote 60 instead of 90. I'm looking at numbers upside down today. I'm going to change the color to purple so it shows up a little better. Okay, you can see what happened here. I got my 4 lines, but it's pretty obvious from my output that I had the angle wrong. Now, if I had had that all written out, I would have to go and change every single left turn from 60 to 90. Here, I only have to change it once, run it again, and I've got my square. So, again, these visual type of outputs are very good training for how you're working with not just creating the loop, but how you can go in and fix code that's giving you a problem that will be repeated. There's the 3 exercises, and you're drawing different polygons. And you might have noticed that if you take 360 degrees, which is the angle of a full circle, and divide it by the number of sides, you're going to get the angle that you want for the regular polygon. So, for example, here's a hexagon. It's got 6 sides, and if you take 360 degrees and divide it by 6, you get 60. Now, in the full course, you start working with parameters, and it's pretty neat because you can write a general loop for all regular polygons and input the number of sides, and it'll calculate the angle turns. So we're not doing that in the sample here, but just letting you know that you can really build on what you're learning here. The next example is one where the sides are not all the same length. This is a rectangle, and in this case you're going to have more commands inside your loop because they're not identical. You're not going the same distance this time, you're going different distances, so you do need to write all 4 lines to make 2 sides. And same thing with a Tetris piece, and you can rebuild that with loops. Again, if it's more complex pattern, you want to kind of trace out what you got here and then see if it does it again. And there's a repeating pattern of 2 for the main loops. I like the way the discussion is built here. It takes the original code and it puts a space between the repeated patterns so you can examine them. As it mentions here, there's an extra left on the end added on line 20, and that's so that these patterns match. You don't need it to close the figure, but it doesn't hurt. All you're doing is repositioning Tina after she's finished drawing the last line. But now we have a perfect match between the two pieces, and we know we can write a repeat loop of 2 to shorten the code to just the repeat loop with these lines of code, and then get rid of this extra iteration of the same pattern. Now I noticed this, and you may have noticed it too, that you have another repeated pattern inside that repeated pattern. You got Tina go 10, left 90, repeated twice, and you can actually write a little bit more efficient program by using an inside loop. And these are called nested loops. One loop's inside the other. So as this loop goes through, it runs these commands and it hits this loop. It'll loop this twice and then go back and run the whole thing again. It's fun to step through a program like this and see how it works. In fact, I'm going to do that right now. Oh, I actually wrote it that way. Okay, so if I step through, you'll see how it behaves. Okay, there's Tina. She's got a color change. Now we're starting. I'm going to zoom that out a bit. There we go. So now we're starting our outside loop. And you can see she's going and then turning, and then going 10, and then turning right. And now it's going to start executing this inside loop twice. 1, 2. There you go. So now it's going back to the outer loop, and it'll do the same thing. It'll go through those commands and then double up these two commands. So anyway, I just thought you might like to see how that works. Okay, and then you have a task to create a Swiss cross, but you might not be sure about what you're repeating. You're starting at 0, so you're repeating this little zigzag here. There's no reason to start it anywhere else, but for instance, if you started it here at x equals 0 and y equals 30, then your repeated pattern would look like this. It would look like this little U shape. That's just a couple of different ways to see the pattern. If you started it with the U shape, your whole Swiss cross would be located slightly differently on the grid. There's the solution discussion. And then you have one more task, and this one actually has a simpler pattern because these are all V's, and in this case you're setting the angle first and then you're moving. Okay, so that brings us to the end of loops. Go ahead and try out the last 3 levels. These are primarily demonstrations, so you'll see the code jumps quite a bit in complexity. We'll take a look at that after you've had a chance to go through them on your own. Have fun with them. You'll see what you can do with Python and what you can draw with a Python turtle. We'll see you in about 15 minutes. Welcome back, everyone. I hope you had some fun taking a look at these last 3 levels. This time you're strictly an observer, and maybe you had some questions about what the program was doing on each line, or you might recognize some of the programming features that you've already learned so far in this mini course. So this is where the turtle is not just making a drawing, but it's also behaving like what we call an autonomous robot that has sensors. If you remember at the beginning, we talked about the primitive turtle robots that had a sensor in front, and eventually they built more sensors. One sensor is a sensor that is underneath. In effect, it's on the belly of the turtle, and it senses what the turtle walks over. So you can do a lot with the turtle. You can get the location. Remember, this is a grid here, so all coordinates are grid based, and we're going to just call them GPS coordinates for now. They're X and Y based on the grid, and those can be stored. In programming, you have containers for data, and one of the main ones we use are lists, and that allows you to store information as you're going. You just add it to a list, and by the end of it you have a nice full list of sequential information. In these examples, she's detecting if there's a color on the ground beneath her. So if she's traveling across open space, she's not detecting anything. But the moment she's on top of a color, that can trigger part of a program. And we'll even see that she can detect an exact color underneath. The other thing she's doing is using what's equivalent to a LiDAR sensor. Now, LiDAR sensors have been used in some autonomous cars, and it's basically sending out a light beam to an object and measuring the distance by how that bounces back. So it's a very fast way to measure a distance to an object before you run into it. That's why they use them in cars. So all of that means that she can do things like read barcodes or symbols, because what are barcodes? They're black lines and essentially empty lines in between. So if you're traveling across that, you're either sensing the color or you're sensing the absence of color. She can look for objects. She can draw maps. She can follow lines on the ground. Some of you might have done a very basic robotic class, say in high school or with a club or perhaps university, where you had a white line and a little mechanical robot that used that white line on the ground to keep it on track. She can also avoid objects, and this is where the LiDAR comes in. Is like you can detect it before you hit it. And that allows her to navigate through unknown mazes. Now, a maze, of course, is something that's a bit artificial. It's a human representation. But a real life example might be that you go into a building that's collapsed with a robot, and the robot can map out the void spaces, might even be able to detect if there's someone still in there for rescue purposes. It can explore old caves. I think they're using them in places like the pyramids to explore the tombs. And so all of these have real life analogies. So in the full course, you learn how to write these programs, but we're going to just take a peek at how these programs can run. So this first one here has a function that's defined. That's what def means, and the function name is follow line. So typically you name a function for what it's doing, and follow line's pretty obvious. It's going to allow the turtle to follow a line, and you can see over here in the viewer there's a line, sort of a T shape. We call that a polyline. A polyline is made up of different line segments. So there's the rules for how she's going to follow. We won't go into that right now. And then the main program, this is going to look very familiar. This is where you create Tina. PU simply means pen up, which means she's picking up her pen. She's not going to draw a line. We don't want her to draw a line because she would then always be detecting a color underneath her, and we want her to find colors. And here we have D, that's going to represent the distance. Right now it's 0. By the end of the program, D will have the total distance for the line. And for an output, we can make a nice statement. So it's not just getting the data, but you're putting it in a very readable form. I am at position, and it gets the coordinates of that position, and it also prints out the length of the polyline. And very often when you're running a program, you want to produce an output that's readable, and you can think of anything on an app on your phone. Anything is going to come back to you in a way that you can read it without knowing anything about programming or trying to decipher a table or anything else. It'll just plain tell you what the results mean. So that's a nice piece of finish work that you can do on your program. Now on the bottom you can see there's the step button, and we've used that a little bit in the code that you wrote. I'm going to step through the program. I might go quickly through some parts and stop at others. You'll notice also there's a little window that pops up when you're in step mode, and that is basically showing you when you're creating an object or a variable and what type it is. So the first thing the program does is says, oh, I'm going to stop. I'm going to register the fact there's a function here. And the program can tell it's a function because of this DEF at the beginning. And then you can see it jumps all the way down here to the main program, because all it wanted to do is say, up, there's a function, I know where it is. We're making our turtle, we're picking up the pen, we're setting the distance as 0 because we're going to add to it. And then on line 15 here, we are now calling this function. So watch what happens. Boom, up to the function. And then it starts working through the function. And you notice that Tina is called T inside the function. That's a local parameter. Local variable, I mean. And every time it computes a segment, it returns it to the program and adds it to the distance. And if it's no longer any more distance, done equals true, then it'll stop calling the function. So we'll just keep calling the function. I'm just going to click through this. Watch what the turtle is doing. You notice that when the turtle gets to the end of a line, it keeps going. And that's because it has to detect that there is no more line. And you see it's checking in both directions. Okay, I can't go this way. Oop, I can keep going this way because there's a line. I'm detecting a color underneath me. And again, it's checking that way, it's checking that way. It's going to turn around because it's not going to go back the way it came from. And same thing, every time it comes to an end of a line, it keeps going. It says up, empty space, back up. All right, so it's going to check each time. Up, I can keep going here because there's more line. Back. And there's one last little line segment here. And just making sure there's no more. None that way either. Okay, that means I am done. So now we're going to print out our statements. It says where the turtle is at, and we can verify that. There's the axes, so that's 10, 20, 30 x and 0 y. And the length is 130, and we could confirm that by counting these segments as 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130. Good job, Tina. So this is a robot that's figured out how to do all this stuff on its own. That's what makes it an autonomous robot. In the next task, we're doing something a little different. This time we're navigating the maze, and this is where we use the LiDAR so we don't run into these walls. And we're also looking for, we're going to call them eggs, like Easter eggs. They're different colors. There's a yellow one, a teal one, there's a kind of a light green, a purple, an orange. And we have one that acts like a stop sign. It happens to be red. That's going to stop the process. So when Tina detects red under her belly, she's going to end. And you'll notice the wall has a color as well. And so when she's using her LiDAR, she's looking to detect that color. So let's see how she behaves in this one. Okay, this time we got effectively an egg basket. It's an empty list. That's what the square brackets mean. And you can see this time we're not defining a function. We're just running through one program. We're defining the turtle. We're picking up the pen again because we don't want to draw if we're trying to detect a color. And notice that this loop says while Tina on color is, well, not red. Okay, so she's going to keep going as long as she does not detect red. And then she's also going to be looking for this color that's called wood. That's going to be the wall. And let's see what happens. Okay, we always have to let the whole thing load. All right, there's our empty list. And Tina. And notice that this time we're spawning her. We're not spawning her at 0, 0. We're backing her up minus 10x and 10y. And that positions her facing the entrance of the maze. There she is. Okay, so we don't have red, and we're going, and we're going. Okay. Okay, we're doing this color probe to check each time. And what did we find? Okay, there's the wall color, and you notice that we're looking for something that's 10, an interval of 10 away. So she's sitting here, but she's detecting something that's 10 steps away. So that's the distance. And she knows she got to turn around. Okay, what's happened here? She's got a color. And I'm sorry these are so light on my screen, but that says, I can't see it. It's color probe, I believe. It's a little bit too light on my particular computer. But she is checking for color. Okay, and it says the color is not equal to none, so we do have a color, and the color is not equal to red. So now what's going to happen is she's going to add it to our eggs list, and that's what eggs append mean. Okay, there's our list. She's adding it to the list. She's getting the coordinates, so get x means she's going to get the x coordinate of that egg. She's also going to get the y coordinate of that egg, and she's going to pick up the color. And if you look at what she picked up here, it's the color yellow, and it's represented by an RGB code where it's a full-on yellow. The R and the G are both the full value of 255. The blue is 0. I know it doesn't make sense that red and green make yellow, but it does in RGB, in the world of RGB. So here we go, and I'll just keep clicking through. You can always go back and play with this again when you're on your own. And very nicely avoiding crashing into the wall so far. She's checking. She can keep going. She's picking up another egg. I'm recording this location again. All right, here we go. We're going to hit this red egg here. Okay, so, oh, we found something. Okay, is it going to meet this condition this time? No, because it's red. The color is red, so watch what happens. Boom, skip that. We didn't put it in our list. We're actually getting her to check the walls again. And we're done because we hit the red, and that was the stop condition for this while loop. So it jumps out, and we got our display command, and we're going to write a statement about the eggs. So the eggs that were found, and this is going to go back and retrieve all our eggs. So there's our first egg. That was the yellow one at 30x, and that's correct. 10, 20, 30, and then 20y, 10, 20. There's our yellow egg. And there's the color. There's the RGB code for yellow. Okay, and then our next one was at 10 and 40, and that's this cyan color, which is, it's a light cyan, and that's what represents the color. And then we had a nice light green at 50-50, and finally at 70-30 we had this, I suppose what it is dark magenta. It's a purple color. And one more, which is an orange. So those are our eggs. And you see that this is flashing stop. That's it. That's all we get. And, whoops, I zoomed out. let's move on to the last example. All right, so if you ever play with fractals, you'll know there's something just fascinating about fractals. It's a very simple mathematical relationship, but it does something that seems magical, and it's used in a lot of applications. Some of the ones that come to mind is understanding branching patterns in plant growth. You can see them in river drainage systems. So there's a lot of natural examples of this mathematical relationship. So this is called the Koch's curve, and when you have it at n equals 0, it's just a straight line. That's all it is. Now, when you make n equals 1, you'll notice that you end up with this angled peak, 60-degree angled peak in the middle. So you're taking this line and you're dividing it in half, and you're moving it the same length, more or less, as this segment up here to a peak. And then the same thing happens with 2. Each of these now has a little peak. You can see that. And then on the next page, 3, same thing. It's dividing again into all these little peaks. And by 4, it's looking quite complex already, even with n equals 4. Now, each time that you add a peak, of course, the actual curve becomes longer, and it explains the relationship here, even though the distance from one end to the other is still the same. So we're going to make a snowflake. There's 3 curves. Remember, n equals 0, and that's n equals 1, where you've made a little peak in the middle of each one, and n equals 2, and n equals 3, and what you're going to draw here is n equals 4. Now, just for your information, this is called a recursive call, when a function calls itself, and it shows you where these calls are. So on line 6, you can see the function name is Koch, and then 6, 8, 10, and 12 all loop back and call it. Okay, let's step through the program and see what it looks like. If you're running this in step mode, just be aware it takes a little time to load all the data. Hang in there for a few seconds. It will eventually get loaded. Okay, so there's my function, and if I hit the step button, it'll jump to the main program. It'll create Tina, and now we're running a loop, and this is familiar to you. You're running it. Remember, we have the 3 sides, so we got to build each one. Okay, there's, all right. It doesn't look like Tina's doing a whole lot, except turning around in circles, but that's partly because these are very tiny lines. Let's see if we can get her to visibly draw anything before we... Oh yeah, you can see one little peak there, and there's another little peak. Okay, there's another one. All right, so I'm just going to run it to the end now. You can see why it takes a while. There's a lot of computation involved. And there's the result. There's the snowflake. All right, well, that gives you a little taste of what you can do with Python and with the Python turtle. Programming is quite amazing. It takes some skill and practice and experience to know how to write a program, what type of coding you're going to do. If you're going to use functions, if you're going to use loops, if you're going to use lists, what kind of detectors you're going to put in there. but it's quite a journey. It's one of those professions that if you fall in love with it, it can be a lifelong profession. It can be a real passion. Um, but you have to start somewhere, and this is a great way to start. If you've taken the Intro to Computer Programming course before, you have an idea what you're heading into when you take Visual Introduction to Python. Now you're typing a little bit more serious code with a lot more flexibility. You still get that nice visual output to help you check how your program is working. And there you have Tina at the bottom of a fractal tree. Once you've completed this sampler course, you get a nice little certificate that you can print out. We do have materials for you as librarians and teachers. If you're running a club or working with a group of people at the library, you can use it as a rough guide. Hopefully, what you can do with something like this is have them do the sampler, and you might divide it the way we did, where you're looking at the basic drawing commands, and then you're looking at the loops, and then you're looking at what that turtle can do. There's some, so you can print out extruded lines as an STL file and practice printing things on a printer. They're fairly small. You can make these as just little artifacts. Like I said, you can make a cookie cutter, or you can just make a little pendant or something that they can wear, where your line width and your extrude thickness should be about the same if you're printing out a pendant. But you can make them pretty small. It's just a fun little token that they can take away with them. And then that last section where you're looking at what you can do with Python, that might be worth doing WebQuest, for example, where you go out and you research LiDAR, or you research robots exploring areas where a person can't go. Good examples, the Mars rover. That's not exactly a friendly environment for humans, but we got this fabulous, it's not just one robot, it's a whole army of robots, right? We think of it as one. We like to personify things, but just using sensors and tools on the Martian landscape and sending back really very nicely detailed information that allows us to study the planet. So there's all kinds of possibilities to explore. Autonomous self-driving cars is another one that you can end the course, this sampler course, with an exploration. And then, if you have some people who want to go and take the full course, they're going to really develop some pretty good programming chops by doing the course. Next up in webinar number 3, we will explore the CAD 1 and CAD 2 sampler mini courses. In these courses, we build models using a simplified script. It's a great way to practice programming and develop visual spatial reasoning. On behalf of NCLab, thank you for participating in this webinar. We hoped you enjoyed working through the samplers. Please reach out with any questions to support@nclab.com. You can also contact me, Sheila Crawford Bunch, at sheila@nclab.com. Thanks to all the libraries for being such a vital part of our communities.